Hi everyone. In the first lecture of NMR spectroscopy, we have discussed the term chemical shift, which gave us the information how the proton in a molecule resonates. So, in this lecture, I am repeating the information provided by an NMR spectrum of a molecule. Proton NMR spectrum of a molecule gives us the information about the number of peaks, which enables us to know about the kinds of protons present in the molecule. Next, the position of peaks, which tell us about the electronic environment of each kind of proton. Third one is the intensity of peaks, which tell us about the number of protons of each kind that are present, and the fourth one is the splitting of peaks into several peaks, which tells us about the environment of the proton with respect to the other nearby protons in the molecule. So now we are discussing each point by using examples. First one, the number of peaks in an NMR spectrum. Consider the molecule ethane. Here, the 3 protons, 2 methyl groups, or the 3 protons in each carbon are same. The first methyl group is in the same chemical environment as the second methyl group. So, all protons are equivalent. We can consider the 6 protons are equivalent, and we can expect only one single signal in an NMR spectrum. Next, I am considering the propane molecule. Here we can check the environment of different groups. First, I am considering the methyl group. According to this methyl group, its environment is the methylene group. Then, I am considering the next methylene group. According to this, the 2 methyl group are the neighbors. So, both of them have different chemical environments, so they should give different signals. And consider these CH3 protons. For them, they are giving the same chemical environment as the left side methyl group. So, we can say that the 2 methyl protons are equivalent and they can give a single signal, and the methylene proton gives another signal. So, we can have 2 signals in the NMR spectrum of propane molecule. Next, I am giving toluene and nitrobenzene. Both are aromatic compounds. Theoretically, there are 3 kinds of aromatic protons. You know, ortho, meta, and para for each of these structures. However, the ring protons are little affected by alkyl group, and they are nearly equivalent. The 5 protons of benzene ring are nearly equivalent when considering alkyl groups. So, in toluene, we will observe 2 peaks. One corresponds to methyl proton and the other corresponds to the aromatic proton, and can give a total of 2 signals. But for nitrobenzene, as the nitro group can influence the different hydrogens, ortho, meta, and para hydrogens differently, as this group can affect. That means it is a famous electron withdrawing group, and this can affect the different kinds of positions of an aromatic ring, so that in this case we have to differentiate the ortho hydrogens, both of them are equal and paired. Next is the meta-hydrogens, they are equal and one para-hydrogen. So in nitrobenzene, we should get 3 signals. This is how the number of peaks helps to know the different kinds of protons in a molecule. Next, we are considering the position of peaks in NMR spectrum. That we have seen through chemical shift value that are highly characteristic. The chemical shifts are highly characteristic of electronic environment of the nuclei that we have discussed in the previous lecture. High chemical shift value. What high chemical shift value means? High chemical shift value means the nuclei is getting high shield, or it is highly shielded, and so that it needs an upfield or increased magnetic field, and the delta value 0 or low delta value, which is the PMS have. It implies it has low delta value means shielding effect, and it needs high amount of magnetic field, and the high delta value, sorry if I have made any mistake, it is low delta, that is according to delta scale, TMS has the 0 delta, which is having a greatest shielding effect, and it needs a high magnetic field, and from towards left, the delta value increases, that is high delta means it's moving towards downfield or de-shielding, that we were have seen in the previous lectures. And therefore I am coming to the next point, which is the intensity of peak in the NMR spectrum. That also we have gone through some example in the previous lecture, as which is nothing but that as the number of protons in the same chemical environment increases, the intensity increases. Now we can consider the same propane. Propane, we know it has 2 different kinds of protons. One is methyl proton and the other is methylene proton, and that is we have seen the previous slide. They have 2 signals. How these 2 signals are seen, that is the 2 methyl groups are equivalent, that is it may have a 6 number of protons. 6:2 or 3:1. You can see a 1:3 or 3:1, which depends only, the intensity depends on the number of protons in the group. Next, we have to discuss the splitting of peaks in NMR spectrum. Now you compare the 2 spectra. Can you find any similarity? Both of these are the NMR spectra of acetaldehyde. In the first one, we can see 2 single peaks, one for methyl proton and the other for the aldehyde proton. And then, but the second spectra, for a single peak is here, the peaks are split into different signals or multiplex. Here, this spectra we have considered the only points as we have discussed, that is the number of peaks depend on different non-equivalent protons, and then the position of peaks. CH3 protons are highly shielded, so that they are near to CMS, and it is far away from TMS, as it is highly de-shielded. And the intensity of peak. The aldehyde proton having only one proton, and the CH3 proton have the intensity ratio 1:3. And in this spectrum, here we are moving to the splitting of peaks. The first spectrum is the low resolution NMR spectrum of acetaldehyde, and next is the high resolution NMR spectrum of acetaldehyde. The high resolution NMR spectra has an advantage that it can make a more clear picture of a molecule. How is it possible? This is by the phenomenon known as spin-spin interaction or spin-spin splitting. When the NMR spectrum of acetaldehyde, high resolution NMR spectrum of acetaldehyde, here I am considering, the peak for CHO and the CH3 group are seen to be split into multiplets. Relative to a proton in CH3 group, a single proton in the CHO group can align in two different ways. This is a spin-spin interaction. These two orientations of CHO proton produce two different local fields at CH3 proton, thus splitting the CH3 proton into two peaks called doublet. Similarly, relative to the aldehyde proton, the three protons of CH3 group can align in 8 different ways, as shown in this figure. That you can easily understand the three spins. They both can be in the upward position, 2 up and 1 down. These 2 up and 1 down positions can arrange in 3 different ways. All are degenerate. And next is 1 up and 2 down. There will be 3 arrangements with these setups, and a 3 downward spin. Here, as you can see that these 3 alignments and these 3 alignments are degenerate. So, the net spin combination of proton in CH3 is 4, having the intensity ratio 1:3:3:3:1. These 4 possible orientations of CH3 protons produce 4 different local fields in CHO and splitting the CHO proton into 4 signals called a quartet. You might feel some difficulty in finding the splitting of proton with respect to the other. But don't worry, you have some general rules about spin-spin interactions which are helpful in calculating the number of lines expected in the NMR spectra. These are, the first one, protons of the same group do not interact among themselves to cause observable splitting. That is, the 3 protons of CH3 group or methylene group or methyl group do not interact with each other. They can give an equivalent signal, one signal. All are equal. Next is, if there are n equivalent protons interact or couple with the protons on an adjacent carbon atom, the resonance peak is split into n plus 1 peaks of signals. That is, the multiplicity of the peak of a group of equivalent protons is determined by the neighboring protons. That you may get from another example. Next rule is that the intensities of the peaks are given by called Pascal's triangle. Some of you may know what the Pascal's triangle is, which is the binomial expansion of 1 plus x raised to n. The relative intensities of these multiplets are given by the coefficients of this binomial expansion. This is the Pascal triangle. How we can find the intensities? That is, first we are writing 1, then left and right 1, 1. Then for writing Pascal triangle in easy way is that you must write 1, 1 in the left and right position. Then you add the 1 and 2, giving 3. Or you can, for the third, you can give 1 in the left side, 1 in the right side, and in the middle you must add 1 plus 1, 2. Then for the next row, you add 1 and 1. Then you must add 1 plus 2, 3 in the middle. Then 2 plus 1, 3 in the middle, and just add the remaining 1. Now, next row, you can do the same thing. First you put 1, then you add 1 plus 3, 4, then 3 plus 3, 6, then 3 plus 1, 4. So, you can easily expand this coefficients and create a Pascal triangle. And when the signal, then there is one signal, it is called a singlet. Then if there is two signals having intensity ratio 1:1, same intensity, it is known as doublet. Then there is 3 signals, it can be have the same intensity ratio 1:2:1 and called a triplet. Then quartet with intensity ratio 1:3:3:1, then quintet, then sextet, then septet, octet, etc. Now, we can consider an NMR spectrum of ethanol. The first observed spectrum in 1951. It is of great importance because it demonstrated the application of NMR to structural elucidation in organic chemistry. It is first observed in Bloch laboratory in 1951. How we interpret this spectrum? Now we are going to apply the rule. First we can see there is 3 different signals. Surely it contains 3 different protons. These groups are all different, in different chemical environments, and the chemical environment of CH3 is different from CH2, which is different from OH. We only consider the nearest neighbor or the adjacent carbon adjacent group only that will be affected or can be taken as the effective interaction, and others are always we are avoiding. So we can bother only about the nearest neighbor. Here, 3 of these kinds of protons are in different environments, so we must expect 3 signals in the proton NMR spectrum of ethanol. And just we can note the position of these 3 signals from TMS. How we can arrange this? Now you should say that is consider the OH protons, as I've already said in the while explaining which acetone, I think acetaldehyde, I think we have discussed about the CHF proton, the low shielding. In the similar way, the OH proton, to the electronegativity of oxygen, the bonded electrons are towards oxygen, so the hydrogen of proton is completely free, as so it is less shielded and it needs less amount of magnetic field, so it moves to downfield. So it has the high delta value, then CH2, since it is nearer to OH, and then CH3. So the position of peaks, that is chemical shift value, will be less for CH3 than CH2 and OH. Now we are jumping to the spin-spin interaction. How we can determine the multiplicity? Consider this CH3. That is by the rule, if n equivalent protons interacting with adjacent carbon, that peak split into n plus 1. That is, for this CH3, the interacting proton is 2 n protons. So this signal should be splitted by n plus 1. So that 2 plus 1 is 3. 3 signals means should be a triplet having the intensity ratio 1:2:1. And by this, how it's drawing should give 3 peaks, one in the intensity ratio 1:2:1. Next, for the methylene group, we shall expect the interaction surely from this proton and from this proton. Since they are unequal, both of OH proton and CH3 proton are different, we should consider it separately so that the number of signals is n1 plus 1 into n2 plus 1. That is 1 plus 1 into 3 plus 1. That will give 8 signals. But you are thinking only 4 signals in methylene. Why only 4 is visible? That is, the 4 signals that can be from the 3 neighboring proton 3 plus 1. Why? Where is this OH group? There is the importance of NMR spectrum in the structural elucidation. That is, this is not the spectrum of a pure ethanol. This is the spectrum of an acidified ethanol. So what is this acidified ethanol? That is ethanol containing some acid. Then the H plus ion of the acid catalyzes the exchange of protons between OH groups of different molecules. That is, we are not taking one molecule for analysis. We always take a sample. It must contain this number of ethanol molecules. So the H plus ion of the acid, acidified acid medium, exchanges the protons between the OH groups of different molecules so that the lifetime of an OH proton in any given conformation becomes too short to permit the observation of the effect of OH proton on the neighboring group. In other words, there is no spin-spin interaction between OH proton to the other proton as the OH is not getting enough time at stable. So, in the high resolution NMR spectrum of acidified ethanol consists of an OH singlet. That is, OH is not getting enough time, so it should not affect the 2 protons of CH2 also. It should always give a singlet, and then the CH2 proton will interact only with the CH3 protons, 3 plus 1, 4 signals only we are getting, which is in the ratio 1:3:3:1, and it's a quartet and a CH3 triplet. The proton NMR spectrum of pure ethanol is however different. Here, because of the absence of H plus catalyst, the OH proton does not undergo any exchange between the OH groups of different ethanol molecules. So, the OH group is always stable and it can interact with the neighboring group. And the NMR spectrum of pure ethanol consists of 3 lines or triplets for OH due to the 2 protons of CH2 group and 8 lines in the CH2 group, that is octet for CH2 and a triplet for CH3. Now we'll do a problem, that is predict the low resolution NMR spectrum and the high resolution NMR spectrum of methyl acetate. Students, the discussed ethanol spectrum is very important for you, and you should study that well, and the different splitting and the position of peak is necessary. Now you can better understand by doing this problem also. I am giving methyl acetate. This is the methyl acetate, you all know. How many different kinds of protons, or are these two CH3 groups are equivalent? What are you thinking? Can it be equivalent? No. It must not be equivalent because this CH3 group is attached to the CO group and this CH3 group attached to the oxygen group. So, both of them are surely different, though they are not equal, they are non-equivalent. Then, what about its splitting? As if there is any possibility for splitting spin-spin interaction? Exactly, no. There is no way for spin-spin interaction as the non-equivalent protons are far apart. They are not close to each other. So there is no spin-spin interaction. So there will be two signals. They both are different, but they both give two single signals. And in the high resolution as well as low resolution NMR spectrum, we will get only singlets. This is only for you in this NMR spectroscopy, and I hope you understand the splitting of signals, position of signals as well as intensity, etc. This is the end of this basics of NMR spectroscopy. Thank you very much, dear students.